Welcome everybody. Today is special because we have a guest lecture, so we are basically done with the material. And since we've looked at tables, trees, cubes, and graphs, now it's time to wrap up a little bit with our guests from the industry, from Oracle Labs. We'll have three speakers. We'll have Vlad Haprian, who is a research manager at Oracle, has a bachelor's and master's degree from EPFL. He's a specialist of scalable graph databases, meaning that he knows how to shard and scale up a graph database. That's the part I left open last week. And so Vlad will tell you a lot about this. Then we have Lucas Braun right here. So Dr. Braun did his PhD at ETH, actually in the same group as I was. So we actually know each other quite well. So Lucas is a technical consultant. I'm not sure of the order of the
consulting technical program manager.
Consulting technical program manager at Oracle. So he does the link with the universities, collaborations, internships. He might actually have a few words at the end for you. And he's also part of the multi-language engine at Oracle, where they use languages like JavaScript, Python, R, and so on. So of course, that's the physical level that we're talking about, right? So this is how you implement and optimize the database in order to expose to the user on the higher levels, the more abstract logical model. And then we have Julian Donchev on Zoom. Hi, Julian.
Hello, good morning.
Hello. Julian is also at Oracle. Previously, he has a lot of experience with the Oracle database. He was at Accenture, I think, as the global database manager, and previously even at Nokia, where I think, if I'm correct, Julian, you had like 2,300 database systems to manage.
Yes.
Is that correct? Yes. So you're really an expert of Oracle databases. So I think this is the introduction. We have three great people today. So now we'll leave the words to Lucas, and I'll give to you the microphone, Vlad.
Thank you, Gislain, for this kind introduction. I think it saves us the first 3 slides. So yes, that's me. As I said, like I was at ETH for quite a while myself, for bachelor, master, PhD, and even teaching degree. We have Julian on Zoom, and we have Vlad right here, getting ready with the microphone. I just have this one slide to kind of set the stage and tell you what's the overall topic of this talk. And I will have a few slides in the end, if we still have time, to also very quickly tell you what else we do in Oracle Labs and like the internship program we have and kind of the advertisement block in the end, right? So Oracle has this vision, and it's not only a vision, it's actually a reality as well, called converged database. So the idea is really to have one database, one copy of the data, and then different ways of accessing it. So we much advocate having this approach rather than, you know, having your transaction processing and then some processes that extract data there and put it into a data warehouse where it can be queried, or into some other graph database or whatever. The technology that we have offers to have all data in one place and then just different ways of accessing it. That means on disk, data always looks the same, but once we load it in memory, we can have different representations. And for the consumers of that data, we have different APIs. And that's what, so that we can cater all kinds of application developers, right? Whether they are used to use plain old SQL, or whether they prefer using a graph query language, or whether they prefer using Oracle database as a document store. It all works in the same database. By the way, some of you who are looking at what's going on in the AI industry and all these things around generative AI, they might have heard of vector databases too. So the vector databases are databases specialized for storing vectors, and then for querying those vectors using specialized algorithms for proximity measures, right? So I give you a query vector, and I would like to get all the vectors in that vector database that are close to this vector. These kinds of things. We also integrated this into the normal Oracle database, such that you can use vectors alongside traditional relational data, alongside graphs, alongside JSON, and everything. So that's what today's talk is basically about. So Oracle database, as almost any database, offers relational views that you probably know from your bachelor studies. It offers analytical views, also called OLAP queues, which you also, I think, had in this lecture. But since 23C, which is Oracle's newest release, we also support JSON duality views so that you can access data in this not only relational, but document API model that Julian will talk more about. And you can also access data as graph, and that's what Vlad will talk about. So with that, I'll hand it over to Julian for showing you the JSON part of things in Oracle Database 23C.
Thank you very much. Hello, everyone. So you're sharing the slides, right? They're visible to everyone. Or should I share mine?
You can share yours, or,
Right.
or I can share whatever works better.
Let me do it like that. It's easier to share mine, then I can change the slides easier.
Okay.
Let me know when you see them.
Yeah, we see them.
Excellent. All right, so good morning, everyone. And I am Julian Donchev. I'm based in Helsinki, in Finland. At Oracle, I am responsible for PL/SQL and JSON. I'm the product manager for those two products. PL/SQL is, as you know, probably the programming language of Oracle. By education, I'm a mathematician. I graduated mathematics in the early 90s at University of Helsinki, and I even taught mathematics at the university for a few years. I run a blog on the internet called juliandonchev.wordpress.com. It's a database blog, primarily oriented on Oracle databases, but covers different databases. You can just Google for it, you'll find it easily. The presentation I'm going to deliver today in the next 10-15 minutes is about JSON in the database, and primarily of how you can view the data in two ways. How you can view the data as JSON documents, or you can view it as relational. And that's why the views that are the new concept of 23C, that is why they're called the relational duality views, because they can represent a dual view of the data. So I'll show you the examples how you can see it as a relational, meaning in tables, in the traditional relational format. And you can, through the view, you can see the data also in JSON format, as documents. And initially, JSON, some people think that JSON was created somehow as emerging from XML. And of course, there is some connection between the two of them. XML was probably a little bit too complex for many developers. And JSON, of course, is very easy compared to XML. But the reason why JSON appeared around 20 years ago was that there was a need for eliminating the need to use in browsers. If you remember Flash and Java applets, if you don't remember them, they were a bit heavy, and there was a need for a real-time communication between the server and the browsers, and that's how JSON appeared. And JSON stands for JavaScript Object Notation. And actually, the name was a little bit discussed in the very beginning, how to code, because for some people it was more of a language, for some people it was a notation. And there were two different names that were suggested, and the one that we use now, JSON, was voted for. The other option was JavaScript markup language, and they chose to call it JavaScript Object Notation because clearly it's more like a notation than a language. What it means is that you can have at most 32 megabytes of data, and it's a different data type in the Oracle database. As you know, in most of the databases, there are different data types. There is number, there's date, there is character in Oracle called varchar. And in the Oracle database, as of now, there are 25 different data types. So for now, JSON is the newest data type. And Oracle is using a native version of so-called OSN. It's the Oracle Optimized Binary JSON format. It's an extension of the standard JSON format because we have added some scalar types. So we have added date and double, and they are not part of the JSON standard. So the OSN format is a bit of an extension of the JSON standard. And the SQL type JSON, it uses the format OSN, which has a significant reason for that. It gives a better query performance. SQL runs faster. And there is another reason that textual JSON data is not needed anymore to be parsed. The way that you use this new data type, and you have to put a compatibility parameter in Oracle. That's one of the parameters which you use to start the Oracle database. And JSON is not the only one data type that is being supported by the database. You can store the data in a string called varchar2. You can store it in a CLOP, or you can store it in a BLOP. LOP means large object, and BLOP is binary large object, and CLOP is character large object. So there are technically 4 different ways to store the data. But JSON data type is a new in 23C, and this is a data type that is probably the one that will be used in the future. Now, as I mentioned in the beginning, the relational duality views can view for them, we can view the data in 2 ways. In order to show you how it works, let me have 2 tables, very short, very small tables, for the sake of showing you the examples on a PowerPoint slide and easy to understand. The top table called celebrities has 9 rows.
Julian, we don't see the tables yet. Are you sharing them?
Yes, I am. You don't see them?
It's my computer. What do I have to do? Sorry, one second, Julian.
Yes.
What do I have to do? Switch the window. Oh, okay.
Can you see them?
Now we can see them.
All right, very good. So one table, the top table is called celebrities, and the second table is called fields. Those people that you see on the celebrities table, they're real people. The top 5 ones, they're famous database experts. And the bottom 4, of course, are football players. And we have a column, which is a Boolean type, which is also new in 23C. It's called is-ace, which means that they hold the title of an ace. Ace is a title given to people in the database community who have significant and major contributions to the database community. And we have a column called certs. This is the number of certifications they hold. Of course, football players, usually they don't certify databases. And we have the field number. So that's why we have the field table, which has 3 fields. One is called databases, one is called football, and one is called cinema. And each one has a number, 10, 20, and 30. Also, the celebrities, they have an ID from 1 to 9. And in order to have duality views work, look at the bottom of the slide. You need to have a primary key on the tables. And you need to have a foreign key constraint, which from the celebrities table references the fields table. That's why we are using the field number in both tables. All right. So there is a special syntax on how you create the duality views. And here is the syntax. It might look a bit cryptic in the beginning, but the first line is the creation and the name of the duality view. So it's a create duality view. I give it a name. We call it fields duality view, fields_dv, and we add a select statement. That's it. The syntax is simple, create duality view as select from something. And we select the field number, the field name, the location, and we select the celebrities as JSON. For each celebrity, we add the ID, the name, whether he is an ace, and how many certifications the one carries. We have, as you can see, in the from row, we have with insert, update, delete, which basically means that we can do DML. We can insert, update, and delete the data through the view, which I'll show you also how it is done. All right. So you usually get an error message if the field, the table, does not have a primary or unique key. And you also get another error message if the joining columns do not have a foreign key constraint. So that's why, if I go for a second to the previous slide, that's why I created the primary keys and also the foreign key, as you can see. That is a requirement. That's how it works. All right. And now I want to see what the view data looks like. I select star from fields DV, and at first you get probably a little bit annoyed and surprised because this is unreadable, right? Not very nice. But there is a way to use the keyword pretty to see the real data as JSON. So if I use JSON serialize and I add the pretty keyword, I can see a totally different view compared to the previous slide, which was highly unreadable. And what you can see here is a standard normal JSON document, which of course I cannot put the whole document on one slide, but at the bottom you see for every celebrity, you see the ID, the name Alex, you see the ID, certification number, and so on and so on. In the beginning, you have some metadata. And the metadata contains two different keys. One of them is called as of, which is actually the system change number for the moment the document was retrieved from the database. That is important for data consistency. And you have the ETH, which is actually is a hash. It's generated from the record, from the contents of the record. You can use it for programming and supporting optimistic locking. You can check that the content of the record have not changed since the JSON document was created, because you don't then want to work with the data which was already changed. This is how the data looks like. This is for people who are used to JSON documents. If I don't want to work with relational data, this is the way I'm used to. This is a very simple and straightforward implementation of how you can use the JSON duality view. There is a concept called SODA, which stands for Simple Oracle Database Access. And SODA, you can think of a set of a collection of NoSQL APIs that can let you create and store those documents. We speak mostly of JSON documents, but they can be any documents in the Oracle database. And without any knowledge of SQL, if you don't know any SQL, you can retrieve those documents, you can query them, and this is done in a very simple way through those collections. So a collection, you can think of a set of documents. For example, if you have for every movie, simple example, if you know the IMDb database, for every movie, you have one XML, you have one JSON file, and you can have a collection called movies, where one document is one movie. Alternatively, you can have another collection of different type of documents, say cars. Some, for example, shop which is selling second-hand cars, they can have for every single car, they can have a JSON document, and they can have a collection called cars. And of course, it's not compulsory that you put and order those documents in a special order and you create collections based on some rule. You can have, of course, all the documents in one single collection, which is often not the case, really. But in order to create such a collection based on the JSON relational duality views, you can use a package called DBMS Soda in the Oracle database. That is a system package within the Oracle database. And there is a function. Every package has function and procedures. This is a package that has around 10 different functions. There is one called Create Duality View Collection. And this is an example how you can create a collection. I create a collection based on a fields duality view. So the fields duality view is based on the fields table. If you remember 10, 20, 30, I had 3 or 4 different fields. This is a way how you can create a collection. And I just checked that the collection was created. It's called fields. Now, if I have duality views, we specify the duality view that I can insert, update, and delete data. All right. Let's see how you can insert data through duality views. On the left side, you can see that I'm inserting a new field called development. And I am also inserting a celebrity into that field, another person. And if you want to check that this really happened within the database, you can use standard SQL on the right side to confirm that we have a new person which was added to the table celebrities, and we have a new view called development with number 40 on the right side. So you can do it using values which are a standard JSON document. If you want to update the data, look carefully. I'll go back to the previous slide. Look at the number 10, Haley, where I deliberately missed a Boolean value for is ace. It's null, it's nothing. There is neither true nor false. I'm trying to update the duality view, the syntax on the left side of the slide, I'm updating that is ACE equals true. And I also, at the bottom, for another update, I wanted also to update the field name. From development, I can change it to machine learning. And you can see the result from the top right of the slide. I can select star from fields. I see that I have a new field called number 40 with the name machine learning. This is a way how you can update the data directly through the views. So if you do not want to do it in the traditional relational way using DML, data manipulation language, you can do it using an update directly on the JSON file. And that's very convenient for developers who are not very comfortable, for instance, with relational models, with using SQL or using DML directly onto the database. We can insert the data into the table view either directly using Oracle relational database syntax. This is the one on the left. Or you can use it through the method of updating or inserting directly a JSON file. So you can insert two new values, and you can see on the left side that I'm inserting two celebrities, 11 and 12, Leonardo DiCaprio and Robert De Niro. And if I select the data using JSON serialized from the view, I can see the JSON document is being updated. You can see that there are two new celebrities, 11 and 12, and there is, of course, the field cinema. And of course, the ETH has changed in the document. And I think this was the last slide I have, and I'll hand over now to Lucas.
Before, maybe, is there a question about this first part? So about this JSON duality views, how they work, that you can ask now, that Julian can still answer? An immediate question from the room or on Zoom? Yes, there's a question here. You'll get a microphone to ask it. Let's try. Otherwise, you can have mine. It's fine too. So Julian, we're setting up the room mic. You'll get a question from a student who paid attention. We assume at least.
Where are you? Here?
Okay. Ooh, it gets thrown. Oh, that's fancy. Okay.
I was wondering, when you inserted a document into a new document into the JSON duality views, why you specified the ID field, because that is a primary key. Wouldn't that lead to concurrency issues?
So let me go back to the slide. Let me reshare. Let me share the document. And we are talking about slide which number? The insert?
Yes.
This one?
Yeah. Why you specified ID to be 10?
You don't have to specify the ID to be 10, but this is a primary key. So this is a new ID. I defined the column as primary key in the beginning.
Yeah, I was just wondering if it would be multiple users inserting values.
If yes, if there are multiple values trying to insert the values, then the first one that commits, of course, will succeed. And the second one, which tries to insert the same value, let's say 10, of course, it will get an error message because it will be a conflict with the primary key value.
I guess maybe the question is also, this ID column could be an auto increment, I guess, Julian, right? I mean, you didn't define it that way, but you could.
It can be auto increment, yes. That's how I define it, that just for the sake of simplicity, that I have a values from 1 to 10, but it can be anything. It doesn't have to be like 1, 2, 3, 4, 5, 10.
Right, and if you did that, you would not have to specify the ID, but you could query the document afterwards to retrieve the ID of this newly created record.
It could be automatically created, yes. It doesn't have to be manually inserted. It can be created, for example, from a sequence if you want.
Right, yeah. So at least in SQL insert statements, you have this returning into clause, which would then give you the ID of the newly generated record into an out byte, so you can read it afterwards.
You can read it afterwards and you know what it is, yes, absolutely correct.
Not sure whether the JSON API also allows that, but We have more questions?
Yep, we have one on Zoom.
Oh, great.
If I understand correctly, these views are not materialized, but rather loaded into memory. How does this scale, for example, if you're dealing with large underlying relational tables?
Yes, you're right. Those are not materialized views. Materialized views means a view which actually creates a table. So you can think of a materialized view as a table and it exists as a segment in the database. Those are more like the traditional views. They're not materialized. They don't occupy storage.
And so what do we do for performance, Julian? So does I would assume that the approach still scales, right?
The approach scales, yes. When we talk a big, of course, it's same like with standard views. You can have a standard view defined on a set on tables which might have millions and tens of millions of rows. It is exactly the same. We're defining the metadata. That means the way how the data should be retrieved from the underlying tables. So that scales. That's not an issue. It's very much you can think of the problems that you might have with the standard relational views. You'll probably think of the same performance issues that might arise with JSON relational views. Those are views. They are not materialized. They don't consume space or storage. This is just a metadata definition.
Mm-hmm. Thank you, Julian.
Thank you.
I guess
there's another one.
There's another one. Okay.
Do we have time?
Yeah, we have 2 more minutes, right? Yeah.
How about billions of rows? How are very large databases handled there?
Well, billions of rows usually always bring issues. And then there are several ways that you can tune the performance if your underlying data is stored in tables which contains billions of rows. You can create indexes on those tables. You can create, for example, for every single query, you can create a SQL profile in the Oracle database. There are ways to calculate and compute also the statistics on those tables. So Oracle database offers you a huge set of mechanisms and tools to tune the performance. Big tables are usually partitioned. So when you have a table with say tens of billions of rows, usually I've seen that those tables are partitioned, even sub-partitioned. And of course, then the view is only the metadata definition on top of that data. So you usually tune the statements that are related to the tables with millions of rows. There is no direct way to run a tuning on a relational duality view. It's the same like there is no direct way to tune a standard view. It's just a definition of how to extract the data from the underlying tables.
Thank you, Julian. So
Thank
that's
you.
great questions. I guess we have to continue in the interest of time to also have some time for graphs, but thank you for participating. These are great questions. So I'll hand it over to Vlad for the second part and the graph property views.
Yes, I have to turn on my mic, right?
Yes.
Hello, can you hear me? Amazing.
So we'll start over here, I guess.
Right. So yeah, hi everyone. I'm Vlad. So like Gislan already introduced me, I'm working on graph technology at Oracle. One of the main goals there is to put this technology in the Oracle database. So you get the database and you can use all the models into one piece of software. So I'll talk a bit about general introduction on graphs. Then I will share with you what is available in Oracle database starting 23C. And then I'll try to share some quick ingredients for performance. Okay.
You can just unpin the camera maybe to show the slides. I want to present on the PowerPoint. Yes. Yeah, I guess we have
I love our friend Murphy. No, we're not even getting back to the PowerPoint here. Right. I don't even see where the PowerPoint window is going. That's not good. Oh, it's showing on the second screen.
Maybe you can just share the second screen with Zoom.
Otherwise, you can export as a PDF and show in preview.
So, okay, now all I have to make sure is that I share my window. Gosh. That is not open. Right. No. Let's see. Share screen. I share screen, and now I do this one.
Yeah.
Okay.
So is it better?
I hope it's better now. Is it better now? Okay, cool.
Okay.
Sorry for that.
Right. So first of all, I just want to talk about graphs and why they're important. So graph is really about connections, right? And then you can find connections everywhere around you. So you can think at your social network, at your, bank transactions, the transportation network you're using. They are all basically connections. And then graph basically give you a powerful tool to leverage information stored in these connections. And it's not only me or Oracle who says graph is important. You can find many articles at analyst companies like Gartner, who basically classify graph as one of the top trends in data and analytics. And the main reason for that is that because graph really gives you an intuitive abstraction to traverse connections, right? So I'll show a bit more about that intuitiveness later. Okay. So what is a property graph? This is very simplified. It's a collection of vertices, right? A set of vertices, like you see here, these 4 ones, connected via edges. And then on top of this, you have 2 things. You have labels, which basically describe the type of a vertex or of an edge. And each of these labels, they can have an attribute, which is called a key value pair. So this is a property that every label can have. And because every vertex and edge can have a label, then implicitly every vertex or edge can have a property. So this is why it's called a property graph. And how is this different than a relational model? So here's the key difference, I feel, and it's actually a good difference because the 2 models are very complementary. So in relational model, you have connections which are encoded implicitly as a primary foreign key. So it's actually a bit harder to see them. While in graph, they are encoded explicitly like edges. So you immediately see that, vertex 100 is connected to vertex 300, and so on and so forth. While in a relational model, you actually see just the primary key foreign key relationship. So it's harder to make value of that. For example, so look at these 3 tables, which is about, so you have customers who have accounts, and then you have money transfer between those accounts, right? And then I want to answer a few questions. For example, are Bob and Charlie somehow related, right? Are they transferring money between each other? Or even more interesting, like, is there any money flowing in cycles into this data, right? So cycles means potential money laundering, right? Because I try to hide money through some cycle of transactions. So if you look at these tables, it's very hard to see this information. While if you kind of model the data as a graph, where again, like a primary key foreign key relationship become edges between rows which are vertices, then immediately these questions become much easier to answer, right? Because I can immediately see that Bob is connected to Charlie via this blue pad. So Bob has account for 1, and then there is a money transfer via some accounts that end up into an account owned by Charlie. And same for the second question, you can actually see that there is this kind of strange money flow originating from Alice and ending back in Alice. So maybe Alice is a financial criminal or something. So yeah, so I hope I convince you about why, just from a very high level point of view, why it's easier to see data with graphs and with relational. So what we are doing at Oracle, so we have delivered in a latest Oracle release, 23C, support for property graphs. So what we have done is we have extended SQL with support for graph. This extension is standardized. It's called SQL PGQ. And it basically allows you to do two things: create a property graph view on top of relational data. So again, it's a view like I've seen before, a JSON duality view. And then once you have the view created, we'll have a new operator called graph table, which appears in the from clause of the SQL query, which will basically allow you to query your graph. So pretty quickly, let's have this example where you have customers essentially buying movies, so three tables. It's pretty obvious, like customer and movies would become vertices, and the customer sales relationship would be the edges that connect, right? So how do you define the graph? We have this new DDL syntax, which basically allows you to specify the name of the graph here, movie rentals. Then there are two key things here, like vertex tables and edge tables. So you have to specify which of the tables from your relational data are vertex tables, here customers and movies, and which of the tables are edge tables, here customer sales. And then obviously for every edge table, you have to specify direction, like what is the source, what is the destination. So in the most simplest form, this is how you define the graph. Again, this is a view. It doesn't do any data copy. So in your database, your relational data is kept transactional consistent, and all these updates are immediately reflected in your graph. And then, yeah, obviously there is a more advanced version of this DDL that allows you to basically specify if you want to use a different key for your vertices than the primary key, or you want to expose less columns as properties than all the columns in the table, you can do that. So I won't explain this in detail just for the sake of time. I'll let you go over slides later. And then for querying it, it's this graph table operator, which is about matching paths. So the key thing here is that it appears in the from clause. The result is a table. That's why it's called graph table. So it can be queried by the rest of the SQL. So you can do order by, group by, you can do join on top, so on and so forth. And the key part here is the match. So match is basically, it allows you to define the shape of patterns you want to find in your data, triangles, circles, or stars or something. I'll give a brief example later. So for example, if you want to find, let's say you want to find two customers who bought the same movie with some conditions, right? Movie rental date can be after some date, and movie type can be a romantic comedy or something. So the key part here is the match pattern. So the way you do that is, oops, sorry for that. The way you do that is you specify a vertex, which is here customer 1, connected via an edge, E1, to a movie called movie, to which another vertex, customer 2, is connected, right? So with just a few brackets and some words, it's very easy to define what you want. That's the key idea of graph. And then the columns clause, basically, you define what you actually want to project in the rest of the SQL from those vertices, like what properties from every vertex and edge. And the where condition is obvious. It's just like any where condition in SQL, right? So yeah, so graph makes it very easy to define patterns that you want to look for in your data, so you can extract more value. Obviously, if you're a SQL developer, or you actually know SQL very well, you might ask, why should I write graph when I can just write the 3 or 4 joins that are equivalent to this query? The reason for that is, depending on your schema and your patterns that you're traversing. So for example, here I'm trying to find all the triangles in my graph, A, B, C, and then back to A with any edge direction. The equivalent SQL is actually huge. It's I could even put it on the slide, right? So it's basically this query plus 13 times unionals with more or less the similar query. So the equivalent SQL really becomes huge. Okay, so yeah, so graph, this is what is available in 23C. It's complementary with all the other models that exist there, relational, JSON, and graph, right? So only 5 minutes left. I'll talk. How much time do you need, Lucas? Okay. Okay. So then let's discuss some ingredients for performance. So everything I showed before, basically, the naive way to execute it is you take that graph query, you translate it to SQL, and you let the database execute it the way it knows how to execute SQL, right? But you can do something more. You can actually store your graph in memory, build some specialized index representation for your graph, and then have some specialized operators that can leverage that in-memory representation to do the vertex and neighbor traversal, right? So what is that in-memory representation? Well, you might have heard about it in your discourse or previous classes. There are multiple options. So one option is the agency matrix, where you basically have a matrix where, for every cell ij, you put a 1 if vertex I is connected with vertex j and 0 otherwise. Yeah, this is good representation, but it really takes a lot of space if the graph is sparse, because that matrix will be full of 0. So you can actually improve by storing your graph as an agency list. So for every vertex here, 0, you can actually have a list of its neighbors, 2 and 3. So this obviously solves these problems of space wastage on sparse graphs. But it brings another problem. So if you want to go from 0 to 2 to 3, right? Then you have to start here. You go to, from this data structure, you go to this data structure. Then you come back to this data structure. Then you go to this data structure. So it's really a hop between data structures, which can and will potentially break your memory locality, which is, not great. So the alternative is to try to, compact things even a bit more. So you get even more memory locality when you traverse your graph. And the representation there is something which is called CSR, compressed sparse row. There are a lot of mathematics behind it, but essentially it's a very compressed representation of the original agency matrix. And what it does is, so you have 2 arrays, source and destination. The first array is indexed by the vertex ID, right? So if I want to look for information on vertex 0, I have to read at position 0. And the value that I read is basically an offset where my neighbors start in the destination array. So the way you read this, for example, for vertex 0, my neighbors start at position 0 and they end at position where the neighbors of the next vertex start, so basically at position 2. So you can see here, vertex 0 has 2 neighbors, 2 and 3. So now when I traverse, so my traversal will be just about, reading these 2 in-memory arrays. So I start at 0, I find, okay, the neighbors are 2 and 3. I go to 2. Okay, let's explore the first neighbor. So who are the neighbors of my first neighbor? I come here at position 2. And then, okay, the neighbor started at 4, they end at 6. So I got position 4 in the destination array. And I find the first neighbor, which is 3. So the traversal is much more compact. You can keep these things in memory and get better performance. And then, obviously, once you have that, you can have operators. So instead of doing a join to go from A to B, you can actually directly use this in-memory index, which is basically about looking who are my neighbors in the index. So here for 0 you would find 2 and 3, and for 1 you would find 0 and 3. And yeah, I think that's my last slide. So thank you everyone, and I let Lucas to do some talk as well.
Sure. I guess for this one, we'll have to handle questions after the lecture in the break, or you can also send us email or send email to Dr. Furni, who will kind of then forward it to us. I wanted to have a quick glimpse into Oracle Lab Zurich. So that's the 4 pillars we build upon. If you've seen other guest lectures from us, or if you visit us with the VIS, you will see this slide again. Right, so we do all kinds of research, but we always need a vision how Oracle eventually at least will make money with our research. So it's not that we can just do whatever we like, but there needs to be some kind of a business perspective. We are active in many locations. Zurich is the biggest one. And yes, here's the webpage for the internships and the email address with which you can apply. It's also going to be in the slides. And that was it from us. Thank you for being with us today.